Hello, everyone. My name is Elke Weber. I'm the Gerhard Endlinger Professor of Energy and the Environment and also professor in the School of International and Public Affairs and CMIP3. It's my distinct pleasure to introduce Catherine Hayhoe, our Bradford seminar speaker today. Catherine is a political science endowed professor in public policy and public law at Texas Tech University, where she co-directs the Climate Center. Just earlier this month, she was also appointed as the chief scientist at the Nature Conservancy. Catherine is a native of Canada, and she holds a BS in astronomy and physics from the University of Toronto and a master's and PhD in atmospheric science from the University of Illinois at Urbana-Champaign. In her research in atmospheric science, she develops high-resolution climate projections that downscale global climate models to understand what climate change means locally for people and for the natural environment. She has published widely on this, including a co-authored forthcoming Cambridge University Press book. Catherine has served as a lead author for the second, third, and fourth US national climate assessments. She's also received many honors, too many to mention, but including the American Geophysical Union's Climate Communication Prize, the Sierra Club's Distinguished Service Award, and has been recognized as a United Nations Champion of the Earth in Science and Innovation. She's been on my radar screen for a long time, probably since I read her 2009 book on global warming facts for faith-based decisions. The Nature Conservancy announcement of Catherine's appointment to chief scientist lauds her for her impeccable academic record, energetic leadership, and grounded optimism. We are very grateful that she has agreed to talk to us today on connecting local climate impacts to global policy targets. Take it away, Catherine.
Thank you so much for that kind introduction. It is such a pleasure to be with you here today. I'm going to be giving the seminar, and you can enter your questions at any time in the Q&A box. At the end, Elke and I will be taking your questions. You can either ask them live or we will take them written from Q&A. So go ahead and do that anytime. This is an academic seminar, but it's going to be a little bit of an unusual academic seminar. Rather than focusing on one specific study or paper or even a set of or series of papers I've done, this really addresses the bigger question of how do we connect a global issue like climate change to the local scale. And along the way, I'll be showing you many examples of my own work, my own research and publications, and many others too. But I wanted to put it together into that larger frame to remind all of us, every single one of us, what it is that we're doing and how each of our work and each of our effort plays into the ultimate goal of addressing climate change at the time scale and with responses at the magnitude of what is needed to avoid truly dangerous change. So, connecting global change to local impacts. I wanted to start with talking about where we are. And often I find the people who have the most realistic perspective on where we are the paleoclimate scientists. Too often our short human lifespan sort of leads us into being a little bit like a frog in the boiling water, where we're like, oh, the temperature's always been like this, it's not so bad. When we look at the paleoclimate data, though, it provides a rude awakening. And a lot of what I'm presenting here is summarized very nicely in the National Climate Assessment if you want the sources for the figures or the facts. So today, we see that our CO2 levels in the atmosphere have almost reached 420 parts per million. And the last time that occurred was about 15 million years ago. Now, what we've experienced so far is only the transient response. When you start looking at the equilibrium response over a century or more, we see that sea level rise, or sea level, I should say, was significantly higher. For example, 125,000 years ago, when temperatures were anywhere between about 0.8 to 2 degrees Celsius warmer than today, ultimately sea level ended up 6 to 9 meters, not feet, above where we are today. And why does that matter? Well, back then there weren't almost 8 billion people on the planet. And of course, 700 million of us live within the low elevation coastal zone. The United Nations, for example, estimates a potential 300 million refugees by 2100 alone. We also know that if our emissions continue to grow over the century and beyond, we would see atmospheric concentrations we haven't experienced in millions of years. And in fact, of course, it's very hard to get detailed information going back that far, but as far as we can tell, the amount of carbon that we humans are putting into the atmosphere on an annual basis has no historical analog. Not only that, but we are living in truly unusual times. If you look at climate variability over the last 100,000 years, and you look at the emergence of modern humans and eventually civilization, you can see that our civilization coincided, not accidentally, with a period of remarkable climatic stability, part of which is likely, not proven, but likely related to human activities, including deforestation and the development of agriculture. We know that regional climatic variations have had significant impacts at the regional scale, whether it is the medieval warm period and the Viking expansion, whether it's the collapse of the Mayan civilization related to drought and deforestation, whether it's other events that have happened in the Middle East. We know that climatic variations have spelled both profit and loss to civilizations in the past. But we know that at the global scale, our entire civilization is largely built on an assumption that we can have hot and cold, wet and dry, but the highs and lows that we've seen in the past and the long-term average are reliable predictors of future conditions. This is what we call stationarity. And almost every aspect of our society is based on the assumption of stationarity. Like what? These are just a few examples. Our residential and building codes, the type of crops we grow, where and when and how, the energy demand that we plan for, where we draw our flood zones, whether we have snow removal equipment or not, our water and energy plans, even the clothes that we have in our closet are predicated on the assumption of climate. But planning for the future based on the past is akin to driving down the road looking in the rearview mirror. If you live out west, where I live, or further west, there are some places where you can get a very far distance down the road looking in the rearview mirror. Why? Because if we're on a straight road, then where we were in the past does tell us where we'll be in the future. But of course, climatically speaking, we are no longer on a straight road. Climate is changing today faster than any time in the history of human civilization on this planet. And that's why it matters. It matters because of us. We have built the vulnerability to climate change into the very fabric of our society and our civilization. And so today, we are on this curve, and I actually went and I found a video that I think is very explanatory. I checked to make sure that no one was harmed in the making of this. This is a real accident, but there was no long-term injuries. You see this bus coming down the hill, and rather than looking ahead, it accidentally hits the curb. This is a metaphor to me of where human civilization is at this time. And so a number of years ago, 5 years ago now, Bob Kopp and I, one of my colleagues from Rutgers, who many of you probably know, we wrote an essay together in Environmental Research Letters where we said Aristotle might argue that humans were not responsible for the changes made at the beginning of the industrial era, when our collective scientific and societal knowledge limited our capacity to choose wisely and well. Regardless of our original ignorance, though, over the last few centuries, we have been conducting an unprecedented experiment with the Earth's climate system, which is the only home that we have. I was fortunate enough to have a front row seat at one of the last lectures given by Stephen Hawking before his death. And as you know, he was an outspoken advocate for climate action and for the risks posed by the impacts of climate change. And so he spoke of this, and I was sitting there nodding along. But then he said something that literally made my jaw drop. He said, and you may have heard this from others too, he said, well, and that's why we have to terraform Mars, because we might not be able to escape the risks of climate change. And I thought to myself, you really think that not only could we terraform Mars, but get a sufficient representation of the population there, not just the Jeff Bezoses and the Elon Musks of the world, but the people who represent the genetic diversity, the cultural diversity, the gender and racial diversity, the socioeconomic diversity that makes our planet what it is and represents true justice. Do we have any chance of actually setting that up on Mars before climate change overwhelms our civilization? The answer is no, we do not. And so when I was, it was a science festival that we were at called Starmus, and my presentation came up 2 days later. I was giving a presentation in the same session as Martin Rees, who, if you're familiar with astrophysics, many of you will know of his work, and my own undergraduate degree is in that field. So he was somebody who I read as an undergraduate as well. And I took the chance to ask him, I said, if you don't mind me asking, do you agree with Hawking about having to terraform Mars to escape from climate change? And I'll never forget what he said. He said, oh, no. He said, Stephen and I are old friends. In fact, they're at the same college in Cambridge. We're old friends, but he doesn't realize that fixing climate change is a dawdle in the park compared to terraforming Mars. So the reality is that this is our home. And this is why we care about climate change, because literally, if we do not fix it, it will fix us. So we know, I took a quick look at what people have been working on here. We know that sometimes the news is a little better than we think. There's a lot of concern about new CMIP6 models being at the higher end of climate sensitivity, and that may not be the case because they might have overestimated some of the aerosol cloud feedback. But on the other hand, we also know that sometimes the news is not great. The fact that climate change is probably increasing the intensity of cyclones like we have suspected for many years. So the science is not giving us a lot of reassurance. And in fact, when Bob and I wrote the final chapter of Volume 1 of NCA, one of our key findings, I think, is really worth highlighting. We concluded that, climate models are our best tool to look to the future. We run them on the most powerful supercomputers we have. We constantly update them with all of the new physics and parameterizations that we find, but we know that they don't have everything in them. And so future changes outside the range projected by the models cannot be ruled out. Moreover, and this is the part that's really scary, when you go back to the paleoclimate record, the systematic tendency of models to underestimate temperature change suggests that they may be more likely to err on the side of under rather than overestimation of long-term change. It isn't the case that this is anything new either. We scientists have been studying this and sounding the alarm for a very long time. From Joseph Fourier, who identified the greenhouse effect, to Eunice Foote and John Tyndall, who independently examined the impact of carbon dioxide and in the case of Tyndall, methane as well, and concluded, for example, in the work of Foote, that if carbon dioxide levels were higher, the planet would be warmer. They did this in the 1850s. And then moving through the century afterwards, we have Arrhenius, who calculated by hand how much warmer every major latitude band of the planet would get if we increase CO2 by 50%, 100%, 150%, or 200%. We've got Guy Callender, who actually tracked 50 years of temperature data to show that the planet was warming due to fossil fuel combustion in 1938. And of course, we have Wally Broecker and all of his colleagues. I could only pick one photo, but Roger Revelle and others too, who in 1965 formally warned President Lyndon B. Johnson of the risks posed by climate change. We scientists have been sounding the alarm for a very, very long time. And yet, here we are. And I love this little graphic here because we've got our sticky notes and we've got our diagrams, we've got our colored pens. Yet, we still remain stuck in the question of what do we do? When we talk about climate change as individuals, we're often told, eat less meat, change your light bulbs, and recycle. And we know instinctively that if we are facing the largest unprecedented experiment we've ever conducted with the only home we have, the light bulbs, the recycling, and not even the meat is gonna fix it. When we think about it scientifically, what do we hear? We hear words like radiative forcing, net zero, and a lot of acronyms that unless you are someone who, like me, works with these acronyms every day, nobody knows what they mean. So when we talk about solutions, either on one hand, we have things that don't seem to address the problem anywhere near the scale, and we talk about solutions on the other hand, and these aren't even solutions in and of themselves, they're just metrics to capture the impact of human actions on the climate, we have sort of impenetrable scientific jargon that we can't really put together. So this is sort of a long preamble to introduce the title of the talk, which is, how do we connect global change to local impacts and to decisions that really can be made? Now, this really is the question that confronts us. And don't get me wrong, I use these acronyms myself, and many of you do all the time. And in fact, in the National Climate Assessment, in Chapter 4 of Volume 1, I went and I wrote a really nice plain language summary of what these acronyms mean. So if you're ever looking for anything to give to your students to try to explain, what were the IS92 scenarios, the SRES, the RCPs, the SSPs, this is a great little resource to kind of untangle those really important concepts that we do need and we do use in science. But in terms of engaging with policymakers, in terms of engaging with decision makers, and in terms of engaging with the public, these concepts really don't cut it. This is no surprise. Scientists, decision makers, policymakers, and politicians have known this for a very long time. So in 1990, when the UN Framework Convention on Climate Change was first laid out, they didn't talk about the IS92 scenarios didn't even quite exist then, did they? But they talked about a common metric. They identified a metric. And what was the initial metric? It was to stabilize greenhouse gas concentrations at a level that would prevent dangerous anthropogenic or human interference with the climate system. And they talked about a time frame. So they initially came up with CO2 equivalent greenhouse gas levels in the atmosphere and a time frame to prevent dangerous impacts. Here's the thing though. Parts per million. If you talk to the average person about parts per million, they'll say, well, what is that even? And not only that, but parts per million plays directly into one of the popular myths on skeptical science. Carbon dioxide is just a trace gas. Oh, there's only 420 parts per million. What's the big deal? Of course, there's a very simple answer to that. There's only 420 parts per million of a white powder that somebody just put in your glass. Are you going to drink it, right? We know instinctively that the amount is not necessarily proportional to its potency. But concentrations in the atmosphere of invisible gases that cannot be measured by any instrument that people easily have access to in their homes or their cars or their buildings or their work life is not an easily accessible metric. It does not connect global change to local impacts. And not only that, but we have a second problem too. And the second problem is ongoing. What is a dangerous level? Because some would argue that we've already reached it. In the Stern review, initially, they said dangerous was 550 parts per million, if you recall, back in 2008. But then others like Jim Hansen and many others who you may know well pushed back and said, no, 550 parts per million is much too high. Maybe 350 is a more reputable or more safe or more scientifically credible threshold of what's dangerous. And 350 has entered common parlance, even though some would say, no, we've already reached a dangerous level today. If you live in a place that's already at risk from thawing permafrost or coastal erosion, they say dangerous has already happened. Organizations like 350 were founded on the idea of we are here and here's where we need to go in parts per million. So what can science do? Well, first of all, we have to recognize our limitations, but second of all, we can recognize what we can do. And we've already touched on our limitations, which is we can't say what's dangerous. The common myth that we have 12, 11, 10, now 9 years left, and scientists say that, is nothing but a myth. There is no magic number. There is no magic threshold. It's like telling people, yes, I can tell you scientifically the exact number of cigarettes that you can smoke without getting lung cancer. That's physically impossible, right? In the same way, some amount of change is already dangerous today to many people in the world. Some other amount of change might become dangerous to others. And even people living in the same place might not agree over what is dangerous, because it depends not only on the amount of change, but how vulnerable they are and how resilient they are, and what their resources look like for adaptation, and what their resources look like just in terms of coping with the changes. So we scientists cannot tell people what's dangerous, and we cannot set any magic threshold where if we get to 1.4999 degrees, everything's fine. But oh, woe betide us if we're at 1.50001 degrees, we're going to hell in a handbasket. That is not science, and science cannot provide that. What can we provide? We can, once people say, is this dangerous? We can quantify the impacts of a specific level of atmospheric concentrations or target, and use this information to let policymakers decide if that's dangerous. And of course, the major uncertainties in this are our scientific understanding of the climate system, including, of course, primarily the feedbacks in the climate system, and our understanding of human choices, because human choices are what is driving this change in the first place. So the traditional approach to figuring out what's dangerous begins at the far end with looking at what choices humans make, and then emissions, and then atmospheric levels of carbon dioxide, and then global and continental change, and then regional and local change, and then climate impacts by system, by sector, and by species. Here's the problem, though. What that does is it leaves you with the widest range of uncertainty at the very end, the information that people are using to make decisions over what's dangerous. And so that is why it wasn't too long after the UNFCCC was signed, maybe about a decade or more, just over a decade, when people started to say, what if we did it a different way? What if we started with a metric that people understand? We have thermometers in our cars. We have thermometers sitting at our kitchen windows. We have weather stations around the world. Everybody understands degrees Celsius, except if you live in the US, but then even here, people understand degrees Fahrenheit, right? What if we started with something as simple as global average temperature change? And what if we worked backwards to look at the emissions associated with a given amount of temperature change? And obviously those have a range of uncertainty due to uncertainty in the carbon cycle. And then what if we looked forward to look at changes in impacts? This was a critical advance in our scientific ability to connect global change to actual decisions that we could make based on what's dangerous. And it started, there's a number of different ways that it started. There was a lot of discussion going on in the literature. I went to a reinsurance company conference, I remember, in China with people like Bill Hare and Stefan Ramsdorf many, many years ago, where they were talking about temperature targets. And then a lot of this information was collected at a workshop in 2005 that was hosted by the DEFRA program in the UK and put into an edited volume. I'm sorry for the low quality of this graphic. This actually came from their website, which many of us contributed to, looking at what dangerous change looks like in many different parts of the world. And then at the global scale, it was really formalized by a National Academy of Sciences report led by Susan Solomon in 2011 that I and many others contributed to. And I want to show you some of these because we don't often realize this goes back this far. It goes back, 15, 20 years. And it really makes sense. So, for example, in that National Academy report from 2011, Claudia Tibaldi created a series of maps looking at how we would expect extremely hot summers to change per degree of warming, how we would expect seasonal precipitation to change per degree of warming. I calculated a number of indicators like demand for air conditioning and the duration of 4-day heat waves. And the maps on the right-hand side, I created these maps looking at how much longer our heat waves would be getting in terms of number of days as the world warmed by 1 or 2 or 3.5 degrees Celsius. Dave Lobel did some really interesting calculations connecting changes in crop yields to degrees of warming. And so you can see, for example, if you are worried about Asian rice, according to these results, then 2 degrees Celsius is not alarming. But if you're concerned about US maize or Indian wheat, for example, then 2 degrees is already very warming, very concerning. So this shows how what's dangerous depends. It depends on your perspective. It depends on where you live. It depends on what matters to you. And so now scientific communication began to tease out the reasons why we can't identify what's dangerous, but we can inform decisions of what's dangerous. And this is what science can and is doing. The big summary graphic for our report is too detailed, so don't try to read all the fine print. But this was really the first attempt to try to put all of this information together in a scientifically accurate but accessible manner. And this approach was also taken in work in California. Originally, our original study was published in 2004, but the work in California went on for the next decade. And they started to try to summarize it with a thermometer. And you can see how much more appealing this is, because you can see, first of all, it's in Fahrenheit, right? Not Celsius. It's in Fahrenheit, and it's showing as California gets warmer, specifically what's going to happen. There's color coding, there's very plain language impacts, and there's degrees temperature associated with it. Of course, the pinnacle, so to speak, so far, of this temperature-based approach was the 1.5 degree report that came out in fall 2018. And they had the updated burning embers diagram, which is, again, another way of tagging impacts to temperature, and concluded that in many areas there was a scientifically robust difference between a 1.5 and a 2 degree warming. This is the type of information that can directly inform decision-making at the national scale, at the international scale, and even at the regional to local scale. You can see that this thermometer approach has carried through. The Climate Action Tracker is a great place to go to monitor the different nationally determined contributions, the INDCs, but you can see that there is no INDC acronym here. What we've got is we've got very clear pledges and targets, current policies, optimistic targets. What do we have? We have a thermometer, and this shows where the world is in meeting the Paris target. So we have, over the last 20 years or more, come a long way in distilling scientific information down into ways that people can directly relate to and directly connect to national and international mitigation targets. Is this a significant improvement in our ability to communicate the risk of human decisions to all who are affected by them? I would say yes, it is. And I actually want to give you one just sort of side note as an interesting example of this. Here's my side note. I was working with colleagues at Iowa State University, which, as you know, has a big ag extension program. They were working with corn farmers. And if you know farmers and producers in Middle America, you know that they tend to be very skeptical about things like the Paris Agreement and climate change. Well, what we did was we went in and we used a crop model that they were very familiar with and that they were comfortable with. We used a crop model to look at corn yields. And this is work that I presented with my colleague, Chris Anderson, at AGU 5 years ago. We looked at crop yields in terms of bushels per acre under the present day, that's the blue bars. And then we looked at it under a 1 degree and a 2 degree warming. We also looked at 1.5, but we're just showing 1 to 2 here. Then we didn't just stop there. We actually talked to farmers about what they would do. We showed them these figures and they said, well, what would you do? And one of the things that farmers said is they said, well, we would increase the number of plants from 30,000 to 32,500 per acre. And so we said, okay, we can actually model that. And we modeled it and we could see that that would actually offset most of the impacts of a 1 degree warming. So they could actually do that. But then we found under a 2 degree warming, they would have to increase up to 45,000 plants per acre. And what that would do is it would significantly increase their volatility of their crop yields. In other words, some years they'd have great years and other years they would have horrible years. The volatility or the variability, as we scientists call it, significantly increased. So without even knowing it, A group of Iowa corn farmers, through using this temperature-based impacts approach, developed their own position on the Paris Agreement targets because we were able to bring them home to the local scale. So have we advanced significantly? The good news is we have. But is this sufficient? Is this enough to communicate the risk of human decisions to all who are affected by them? Unfortunately, the answer to that is no. And so in my last 5 or 6 minutes here, I want to pivot, and don't forget to keep the questions coming. I've seen a few of them popping up in Q&A, but go ahead and put more questions there if you want. In the last part of the seminar, I want to pivot to talking more about the social science of how we as humans absorb and interpret information. We often focus on whether people agree that global warming is happening. And actually, these numbers are even higher now. They're up to 72% as of this year. The majority of people agree that global warming is happening. And these maps, I should point out, are from the Yale program on climate communication. They're really fascinating. You can even zoom in by county and by congressional district if you're interested. Most people agree global warming is happening, and it will harm plants and animals. It will harm future generations. It will harm people in the United States. We start to see more blue here. Blue are counties where less than 50% of people agreed with the question. But we don't think it will affect us personally. This is one of the biggest problems we have. It is something that social scientists call psychological distance. We see climate change as distant in time, affecting the future, not now. Distant in space, affecting people who live far away from us, but not here. Abstract, global average temperature instead of corn yields in Iowa. And we see it as irrelevant to our primary concerns, affecting Greenland ice, Siberian heat waves, or polar bears. This is where we're stuck today. But interestingly, these maps actually hold a clue to our next steps. This is where we left off. Do you think global warming will harm you personally? It's pretty dark blue. If you're curious, just as a side note, why are there some yellow counties? Well, demographically, the two most concerned people groups in the United States about climate impacts are Hispanic Catholics and Native Americans. And you might say, well, of course, that's because the Pope wrote the encyclical 6 years ago. Actually, the least concerned people in the whole United States are white Catholics. They edged out white evangelical Protestants by 1 percentage point in the last poll. Why that is, we can get into later, but the bottom line is it's politics, not religion. But this is the map so far. That's the darkest blue, but there's one that's even darker blue, and here's where we start to see the solution. Nobody's talking about it. So connect the dots here. If nobody talks about it, why would anybody care? And if nobody cares, why would we ever want to fix it? The real solution here is we need to be talking about why and how climate change matters to us. And that's where we scientists can come in. And we need to encourage all the other people who have all the great information on how we can fix it to talk about how climate change is not a boulder sitting at the bottom of the hill waiting to be rolled up, but it's already rolling down the hill in the right direction. There are solutions. So I just want to give you a couple of examples for us as scientists. Here we go. These are going to be very familiar figures to you. But my point is that this figure does not communicate to people on the coast the risk of sea level rise. What does? What does is talking about how sunny day flooding is up to 300 times more frequent in some coastal communities. Or Miami Beach is raising the level of its streets by 2 feet. Or sea level rise has already cost Carolina beach properties $1.6 billion. Or your Florida home could lose 15% of its value, according to Zillow. These are the ways that we connect what we do with what matters to people. We talk about ocean heat content. However, 93% of the heat that's being trapped inside the climate system is going into the ocean. But why does this matter? It matters because ocean heat content affects a whole host of things, like the coral reefs, the nurseries of the ocean, the risk of toxic algae blooms due to pollution, and of course, as many of you study, the impacts on hurricanes. The fact that we see that hurricanes are intensifying faster, getting bigger, stronger, slower. That was Jim Cossen's work just last year. And then talking about how temperature is increasing. It's not just about global temperature. It's about what's happening with our heat records. It's talking about our heat waves. It's talking about the impact on the poorest and most disadvantaged who can't afford to pay their power bills or who have cracked windows or who live in mobile homes. I have colleagues who live in Phoenix who were looking at heat-related mortality and morbidity, illness and death. And my colleague Patricia Solis, she was looking at a map of Phoenix and she saw this one block that was just red, dark red, from heat-related illness and death. And she thought to herself, this must be a mistake. So she pulled up Google Maps, and what do you think she found? She found that that entire block was mobile homes. That entire block, and that's why it was dark red. There is a huge social justice component to extreme heat and vulnerability, and that is part of what we can talk about as well. And then what about the wildfires in California? My cousin's home was burned down. You know people and colleagues who've been affected. We know that climate change isn't causing wildfires, but when those wildfires are ignited by gender reveal fireworks or somebody dropping a load of burning trash into the dry brush, we know that they burn hotter, faster, and further. We know that this isn't just happening in California. We're seeing it in Alaska. We see it in Canada. And it's hard to remember a year ago, but a year ago, just a little over a year ago, the headlines weren't COVID yet. A year ago in January, the headlines were Australia. So talking about why climate change matters to things that matter to us, water, food, safety, economy, our health. This is the next key step. And here's the interesting thing. Look at where we were with COVID back at the beginning of March. That's where we are with climate change in terms of how concerned we are. We are in 55 to 60% of people in the US are concerned about climate change, which is where we were with COVID in the first week in March. Rapid action helps, and that's why we need rapid action on climate change now too. What's holding us back? Well, unfortunately, political polarization is one of the main things. Last February, climate change was, and continued to be for the last 10 years or so, one of the most politically polarized issues in the whole US. Then COVID happened, and you can guess what happened. By the way, the gray bar here indicates the amount of political polarization. The wider the gray bar, the more polarized the issue. This figure doesn't rank by the width of the gray bar, so I'm going to show you number 3, 2, and 1. COVID became the third most politically polarized issue in the country. Race and ethnic inequality became number 2, and at number 1, we still have climate change. So how does this relate to the psychological distance I was just talking about? Well, no matter whether we live in the US or other countries, and I just want to point out these 2 studies to say that this whole political polarization issue is not only a US issue. It is also an issue in many other countries around the world, where education and experience on climate change is dwarfed by values, ideologies, worldviews, and political orientation. How do we overcome this? Interestingly, this is one of my colleagues, Chris Chu, here at Texas Tech. His research indicates that addressing psychological distance, bringing climate change near to us rather than distant and far away, addresses ideological polarization too, because it invokes values that we share that are stronger than values that divide us. So taking that next step and talking about why it matters to us actually helps. What does talking about climate change affect? It actually affects what we see ourselves as, because we talk about what's important to us. And the more ownership we have of an issue, the more we talk about it, the more ownership we have. It changes what people around us think. It changes what social scientists call our social norms, our idea of what's normal in society. It changes our sense of efficacy, the idea that, can we actually make a difference? Could we fix this thing? And that changes our ability and our willingness to act. This is a fascinating social science chain. But it all begins with what? It begins with talking about climate change. And so this is what I want to leave you with. I want to leave you with a challenge. It turns out when it comes to talking about climate change, Religious leaders, broadcast meteorologists, health professionals, military leaders, they are all very respected messengers on climate change. But according to the social science, the second best messenger on climate change is you. Scientists. Scientists are the second best messenger. Now, when I say talking about climate change, your mind might immediately jump to, oh, she's talking about doing congressional hearings. And if you are somebody who enjoys congressional hearings, not sure that most people do, I say more power to you and thank you. I do not enjoy them. And that is not where I prioritize my time. I'm totally fine with telling Anderson Cooper that we scientists are not writing the National Climate Assessment for the paycheck. I have no problem doing that. You might not want to do that either, but are you, does your kid attend a school? Are you part of a place of worship? Are you a member of an organization like the Rotary Club? Are you a birder or a hiker or a walker or a surfer? Do you do something outside with other people? Are you on social media? Like the 3,100 scientists who do climate that I have on this Twitter list that I keep. Whoever we are in a place where we can have conversations about why climate change matters. And we are the number 2 most trusted messengers. Who's number 1? Guess what? It's you too. You are also number 1 because friends and family, people we know who share our values and speak a common language, are also the most trusted messengers when it comes to climate change. The more we trust the messenger, the more concerned we feel about climate change. So what are our conclusions here? We have come a long way already in connecting global change to local impacts in the physical science. We have come a long way in the last 20 years to really zooming in on what climate change means per degree of warming in the places where we live and how that connects to the Paris targets. And the new book I have coming out with Cambridge University Press in about a week or 2, I think. It's actually been delayed by COVID, but I think it's coming out in about a week or 2. I wrote with many people you may know, Rao Kodamarthi, Don Webbles, Linda Mearns, as well as 2 practitioners, Jennifer Jacobs and Jen Hirado, who work with infrastructure engineers and cities in really incorporating climate resilience and mitigation into planning today. So the good news is we've come a long way. But the bad news is we still have a long way to go. We're not there yet. And that's where the social sciences comes in. So in addition to writing that book, I also wrote another book this past year. It comes out in September, and it's all about how do we as individuals and as humans engage with this? How do we get past the divides in our world? And how do we actually have constructive, positive conversations about why climate change really matters, and it is a huge risk, but also how we really, truly can put the brakes on this unprecedented experiment that we're conducting with the only home that we have. Thank you.
Thank you. Thank you so much, Catherine, for telling us so eloquently how we can get people to worry and to talk and hopefully ultimately to act on climate change by making things local and bring them home to them. I'm going to ask you some questions from the audience, but let me sort of maybe start us off by having you reflect a little bit more how action and communication from scientists could or should interact with messaging from other sources. And so science is great, but as you mentioned policymakers, you mentioned NGOs, you're about to take on another role, it's the Nature Conservancy. Foundations. How does it all fit together, and how can we make things sort of more coordinated and therefore messaging more impactful?
I love that question. Thank you so much for asking that. First of all, I want to emphasize that there's a broad spectrum of engagement, and there's no one right place to be. There isn't. And in fact, over the course of your life, you might move up and down or across that spectrum, and that is also perfectly okay. We need scientists doing the science. We need scientists publishing in the discipline-specific peer-reviewed journals. We need scientists doing the review articles that help scientists outside a certain field get a sense of where the field is going. We need scientists contributing to and participating in national climate assessments, regional assessments, IPCC assessments and reports, and more. And all of these are degrees on this spectrum. We need scientists engaging with our local schools and our local educators. We need scientists engaging with our local decision makers in our city or our region or our water district, or people who are making decisions and need this type of information. We need scientists' voices visible on social media. I'm not going on TikTok, but there are scientists who are there, and I say all power to them. We need people at every level. We need people informing the government behind the scenes and in front of the scenes. We need people who are visible, people who are invisible. So there is no one, here's what you need to do, but there are so many opportunities because our voice is trusted. So I think that's kind of message number one. Message number two is this. There's a lot, and of course, okay, you know this more than anyone, there's a lot of social science that has gone into looking at what constitutes effective communication. There are workshops at AGU. There are wonderful books, and I can happy to make recommendations. There are webinars, there are training sessions, there are, of course, many peer-reviewed papers, there are websites that summarize it. There's a lot of great information that shares how to and how not to be effective communicators of climate change in a scientifically responsible way. And so I think it's really important, and I do this myself regularly, is to look for that information and to make sure that we are following best practices or recommended guidelines or just suggestions and ideas on how to talk about climate change effectively, because our time is the most valuable resource we have. It is the most non-renewable resource we have. And so whatever we're going to do, at whatever scale, even if we're going to do, one thing a month or one post on social media, it's really important to be informed by the social science of how we can make a big difference.
Thank you. Melania Guerra had a couple of really good questions. Melania, do you want to mute yourself and ask the question?
Yes, happy to. Hello, Professor Hayhoe. I'm a huge fan of yours on Twitter. I wanted to know, I am originally a scientist and I'm pursuing now a social science degree here at Princeton to complement those two aspects of science communication. So I was wondering first, when you spoke about natural scientists being the most or the second most trusted messenger, I was wondering if social scientists are also as trusted, or does the public differentiate between those two expertises? And furthermore, I was wondering if you can talk a little bit about the downsides or the risks that a scientist assumes when they become vocal. Do we get punished still, by becoming less neutral and being perceived as taking sides? Thank you.
Those are great questions. So I'm going to put a link here in the chat, which is a link to a talk that I gave at Columbia last September, where I talked a lot more about scientists as communicators. So this whole idea of scientists and communication was the subject of one of the talks I gave at Columbia, which has been recorded and is right here. But in brief, you asked very good questions. Regarding physical versus social scientists, I think that depends on whether people even know the difference. And I feel like a lot of times people don't know the difference. But I feel very strongly as a physical scientist with a background in physics and atmospheric science, who now resides in a social science department, political science, I feel very strongly that both physical and social scientists are scientists. And so my Twitter list includes both. And I feel that both of us, both groups, and obviously it's not just two groups, it's a continuum, we absolutely have the basis and legitimacy to call ourselves scientists, which means that we are experts who do quantitative research. So in terms of credibility, I think what often makes things credible is when we actually talk about who we are and what we do. So when people understand, I'm the person who actually goes to the Greenland ice sheet, that actually makes a big difference. But if you could say, I'm the person who actually studies what people think about climate change, and I have all the data, that's also a source of credibility too. So I would say that if we sort of feel that we don't necessarily have that credibility, just remind ourselves, whoever it is that we're talking to, whether it's parents at our kids' school or just our next door neighbor, we have a lot more than they do. And we're also much more familiar with the broader scope of the scientific literature. Now, in terms of credibility, this is a hard issue. Many of you are probably part of, and if you're not, I highly recommend the Earth Science Women's Network. I've been part of it almost since it began. And I remember going to an AGU workshop that ESWN put on a number of years ago, and they had several really good senior scientists giving advice to early career scientists, which I was at the time. And I'll never forget what one of them said. She said, When I first joined my department, I was told that a blog, blogs were popular back in those days, a blog was seen as a charming eccentricity in a senior scientist. But in a early career scientist, it denoted a dangerous lack of focus. They weren't looking at their research, they were looking at blogging. And unfortunately, that's the way it was 15 or 20 years ago. And in some departments, that's still the way it is. But the world is changing. And the fact that there are others leading the way, you know, Jim Hansen was a very early leader in terms of maintaining scientific credibility, but also being very outspoken on climate change. But today there's many more. The AGU actually offers a climate communication prize, and we're pushing them. And if you want to add your voice, you'd be welcome to offer an early career communication prize too, because we think that would be so important to respect the people who are spending their time on it. For many years, NSF actually funded a discourse one-week retreat for early career scientists that focused specifically on communication and engagement in climate. The world really is changing. And honestly, I feel like younger people are leading the way. And so I feel for many of us as mid-career or senior scientists, not only engaging ourselves, but supporting and helping early career scientists who do that too. And as Elke has probably done, and I do too, sometimes our engagement can feed our research. And sometimes our research can feed our engagement. So we don't have to see it as either or. We can kind of see it as overlapping diagrams where we might get new ideas. Sometimes, you know, third graders are some of the smartest people in the world. They might give you a brand new idea you never even had before when you talk to them. So I think that our idea of what we as scientists look like and how we function in our world is starting to change. It isn't where I would like to see it, but I think it is starting to change. Elke, would you like to comment on that just briefly?
No, I think you said it very well. And okay. One quick follow-up question before I get to the two hands that have been up for a while. Christina, do you want to ask your question about the humanities? Christina Gerhardt. Well, okay. You're there?
Well, I can read her question here.
Yeah, okay.
So she was saying, what about humanities? Are they as trusted as natural scientists? Well, so first of all, I would like to say at Texas Tech University, we have a climate center. We have over 50 faculty who are full associates or affiliates with our center, and we have many from humanities. We have artists, musicians, people from English and education, and humanities is absolutely essential because they really help to connect our head to our heart. And so much of what we're missing, I sort of alluded to, but I didn't actually say this in my presentation. We have a lot up here, and we just haven't connected it to down here. And I feel like humanities are key to making that connection, to helping us understand how or why things matter. One of my colleagues, for example, studies our sense of smell and how it relates to our sense of place and what emotions it invokes in us when we have this sense of smell. These types of things are so important. Now, in terms of how they're respected as experts, I'm not sure, because I feel like climate change in the humanities is really an emerging field. We have a literature program in it. There's many art programs in it. And I feel like it should be respected, but it's something that's just getting there. And I don't feel like I know any studies or research that I can comment on, but it's definitely a direction that I would encourage people to head in that area, if that makes sense.
Yeah, let's get to the two questions, the hands up. The first one is from V. Balaji.
Hi, can you hear me?
Yes.
Yes.
Hi, Catherine. Long time since we worked together. Glad to see you again. So my question is, though, not about science. I can understand the issues of political polarization and convincing people and so forth, but there's one other reaction I hear from a lot of people, lay people, which I really fear a lot, which is the reaction to accepting the scope of the problem is perverse. I think humans are very perverse. And the way it works is they create climate change bucket lists, the places that I'm going to visit before they disappear. And air travel is going to become super expensive in a net zero world, so I'm going to fly as much as I can before that happens. How do we deal with perversity?
Well, we are a little bit guilty of that ourselves, aren't we? I know colleagues who have specifically planned summer vacations to Glacier National Park so that they can see the glaciers before they disappear. I mean, this sense of loss is real, and it relates. as you probably know, there's a lot of emerging research now in the field of anxiety and grief related to climate change and all we will lose. And in fact, I was part of a book that came out this fall. I don't know if anybody saw it, but I think, yeah, okay, you're nodding, you did see it. It's called All We Can Save. And it's a collection of over 60 female voices talking about how we feel about what's happening and what can we save and what we're losing. If you haven't seen it or read it, I would strongly recommend it. And I'll put a link here to All We Can Save in the chat. But I think actually, Balaji, that what you're talking about is a little bit of psychological distance still. It's the psychological distance of it's a future issue and it won't affect me. And so I think there again, talking about what is already happening in the places where we live is really important to help bring it home, but that's only half of it. And I didn't talk about the other half because that's not what this presentation is about. But in my TED Talk and a lot of other talks I give, I do talk a lot about the other half. And the other half is what can we do? Because often we don't feel like there's anything we can do. We have no sense of efficacy. So all we can do is go see the glaciers and we can genuinely mourn their loss, but we don't feel like there's anything we can do about it. So really talking about what we can do, which starts with using our voices. And every single one of us has a voice, and our voice is the most powerful thing we have. Using our voices to talk about that and to highlight examples. I'm going to put my TED Talk in here. Highlight examples of what's happening and who is acting and surprising people like army bases and big corporations and conservative politicians, and what's happening at our local scale and how people could get involved in something that's happening here. That really is a big part of the solution. So bringing that issue near and talking about how we can engage, which is something that we as scientists, I mean, that's not what we're trained to do. That's not what we're experts in, but we don't have to be experts. We just have to find out a little bit of what people can do. That's where we can start to address these massive psychological defense mechanisms and disconnects that we have that you pointed out so acutely. Thank you.
Let's move on to Saeed Shakir.
Hi, Professor. Great presentation. I really enjoyed it. Some very good info. I hope to use it very soon. I'm actually calling in this call from Karachi, Pakistan. And I just want your thought or input on this. What would be, is the debate still on as a scientist that there is climate change? Is it real or not? Because in this part of the world, I mean, it's assumed or it's presumed, it's an evolutionary process. So of course it's going to happen. It's a 2,000, 3,000 year process that takes over time. It's the earth, it's how the world was made. And, you know, there's a lot of thread of religion, Islam that plays into it, the concept of God. And, you know, it's accepted to the point where, okay, so it's an evolutionary process. So what's the big deal? And when we watch the media, particularly the US media and the Western media, there's a lot of hue and cry and uproar about climate change. How could you guide people like me of how do you counter argue this evolution dialogue on climate change?
Absolutely.
I hope my question.
Yeah, your question's very clear, and I'm so glad that you asked it, because so often people assume that rejection of science that we scientists have known for over 100 years is a uniquely US phenomena, but you've just pointed out you have it in Pakistan. I'm from Canada, we have it in Canada. The last place I was pre-COVID was Ireland, and I found it in Ireland too, in a pub. We have this defense mechanism. It's a human psychological defense mechanism that we use to push the issue away because it feels too big. It feels insolvable. But if we just say, oh, it's a natural cycle, or it's God, or somebody else will take care of it, or there's nothing we can do, it's an evolutionary process, then that means that we don't have to deal with it. So it's a human defense mechanism. It's not based on science at all. And I put two resources in the chat here, if you're able to see the chat. The Skeptical Science website I briefly showed during my presentation, it lists the most common science-y sounding objections. And I say science-y because they're not really based on science. They just sound scientific. It lists the most common scientific objections. And number one on that list is, it's just natural, it's happened before. I even have a YouTube series, and one of our most watched episodes called Global Weirding. One of our most watched episodes is, isn't it just a natural cycle? And the answer is no. According to natural factors right now, long-term, the Earth should be cooling, not warming. So it's not a natural cycle in any way, shape, or form. And we scientists have known about this, like I said, for about 100 years. In fact, the foundational science goes back 200 years. So why is this idea of denial so common? Why do we see it? As I said, actually, if you remember my PowerPoint presentation here, why do we see it in multiple countries around the world, not just the US? Why do we see that values, ideologies, worldviews, and political orientation are what predict what we think about science? It's because those, again, are our psychological defenses. We feel like there's nothing we can do to fix it. So we just cling to leaders and politicians who say it's not a big deal. There's other things to worry about. It might not even be real, because it's really scary. It is very frightening, and we scientists see that firsthand. But I would like to leave you with this one thing. As my colleague Renee Lertzman, who is a psychologist, says, she says in her TED Talk, which I'll put right in here, that the solution to anxiety is not pulling the covers up over our head and pretending it's not real. The solution is action. When we feel like we can act and we are able to make a difference, that addresses our defense mechanisms in a positive and constructive way. And that's actually what the book I wrote is a lot about too. Thank you.
Well, on this lovely note, I'm afraid we have to bring things to a close because we are out of time. There's still many more questions, and so the conversation will continue. But thank you so much again, Catherine, for being with us today and sharing your thoughts. You're very much